Good evening, ladies and gentlemen. Welcome to Wits University. May I please ask that you switch off your cellular phones or put it on silent. Please also rise as the academic procession enters. You may sit down as soon as they are seated. All right, you can all take your seats. So I'd like to welcome all of you to this wonderful occasion, the inaugural lecture of Professor Simon Mukwembi, and welcome you all to Wits, those of you who are from outside Wits. And I'd also like to welcome all of those online. I'm sure there are many of Prof. Mukwembi's colleagues and students from on really a significant achievement to have now joined the academy. And so what that means, Simon, is that you get to join Senate. And that means that you get to determine where this university is what direction it takes, and you get to make important decisions because that's what Senate is about. But for tonight you are here to profess and to tell us about your wonderful contributions, and to, I guess it's really a lay audience. I know that many of your former students and things are in the audience, but it's to also relate, what your major contribution has been in an easy, digestible format. So we really do look forward to that. And I'd like to welcome Prof. Chetty to do the introductions. Thanks.
Madam Deputy Vice Chancellor, it is my pleasure to present Professor Simon Mukwembi from the School of Mathematics in the Faculty of Science to deliver his inaugural lecture on the topic of From Graph Theory to Drug Design, Predictive Models for Target Identification and Selection. Professor Simon Mukwembi, an awardee of the University of KwaZulu-Natal's 2013 Distinguished Teacher Award, and an award winner of the South African National Excellence in Teaching and Learning in 2014, has many years of experience in research and teaching mathematics at several universities. Professor Mukwembi has over 60 publications with over 1,000 citations. His research in graph theory and applications in developing models that screen and identify compounds suitable for drug design. Professor Mukwembi started his academic career at the University of KwaZulu-Natal in 2006. There he rose through the ranks from lecturer to associate professor. He worked to uplift mathematics teachers' skills. He moved to the University of Zimbabwe in 2015, where he became a full professor, serving as the chairperson of the Department of Mathematics and also as the deputy dean of the Faculty of Science. He pioneered the formation of a university-owned company, which provided connection between the university's academic programs, research and innovation processes, and the addressing of needs of industry, commerce, and society. Professor Mukwembi recently joined the University of the Witwatersrand as a full professor of mathematics, being concerned about the devastating effects of the pandemics such as COVID-19. Professor Mukwembi continues with his research in developing predictive models that screen and identify suitable compounds for drug design. Professor Mukwembi strongly believes in transferring skills to students and society. He's supervising several postgraduate students and has graduated to date 8 PhD students. Madam Deputy Vice-Chancellor, I present to you Professor Simon Mukwembi for his inaugural address.
Professor Young, colleagues, my daughter, Panashre, my family watching online, my classmates, very old classmates indeed, watching online, guests, I would like to say I'm really honored to be here, and I should first of all thank you all for coming to my lecture. Well, I'm going to talk about graph theory to drug design, models, target identification, and selection. Well, maybe my starting point is to say what the concern is. We all know what happened with COVID. I wouldn't want to talk more about problems, but rather I want to talk more about solutions, solving them. We all know what happened with COVID. It's unfortunate that there is speculation that as early as the 2040s, we might have tens of millions of people dying because of pandemics. But while that is so, some researchers actually say, and we see it every day, drugs fail their functions for two main reasons. The first one is that they simply do not work. The second one is that they are not safe. Well, the fundamental question is, from an almost infinite pool of compounds, we have billions and millions of compounds. How do we identify the best compounds? How do we select the best compounds to use for drug manufacturing? That's a very important question. And once we have the drugs, once we have the formulations, we again ask the question, how can we predict the quality degradation over time of these formulations or drugs? So over here, colleagues, I'm going to really talk about linking a fast-growing area called graph theory. I will link it with mathematical modeling and show how it is used in drug discovery. Well, if you don't shake hands with mathematics, please don't panic. Please don't worry. If I were to equate mathematics to a church, I would say today, I'm not going to get inside the church. We may probably walk towards the church. We won't get inside, but we may perhaps touch the walls of the church to have a feel of it. And one other thing that I will also talk about would be the implications of our models. Basically, when I say a model, I just mean a formula the implications of our formulas in the drug discovery, discovering new compounds that treat things like skin cancer and so on. Perhaps, Dean, Prof. Morris, before I begin, let me say I have a history that I would like to share with you. Who is Simon Mukwembi exactly? How did it all begin? Well, my classmates would, of course, agree with me that I grew up in a poor rural area. And some of the activities that I was doing in the rural areas were herding cattle, hunting animals, lions, well, fishing, and working in the fields. You see, these activities actually helped me learn a lot of things. And in particular, I learned when to do things and when not to do things. I also was so fortunate that my grandfather was actually an indigenous medicine practitioner and healer. And basically, I was assisting him in doing his jobs, duty. So he taught me which plants to use, which herbs to use for healing. Now, where is the link between all this I'm saying and mathematics? Unfortunately, even in this rural area, many parents are actually discouraged from letting their children to do mathematics at school because they say, well, they will be taught simultaneous equations and vectors. So those were some of the problems that we were facing. But fortunately, I did maths. And when I passed, it was time to go to the university. And the whole village made contributions. And they bought an outfit for me. And I'm sure my classmates online will be very happy to see this old photograph of me in a new outfit that the village had chased for me. Can you see my slide? Well, colleagues, I'm so sorry. I wasn't aware that you are not seeing the slides, but I'm sure we will be fine very soon. Well, yes, indeed, that was me. That was my first day at the University of Zimbabwe where I got my undergraduate degree. That's the Simon Mukwembi. At the university, I had two worries. The first one being mathematics. The second being diseases, a threat to humankind. I never liked diseases. I did my undergrad, I completed. I did my master's, I completed. I did my PhD, I completed. And then that worry of the threat to humankind actually made me practice. Remember, I was helping my grandparent. So I started practicing. Those were some of the things that I was doing in my practice. I had a clinic called Men's Phyto Medical Center, where I was handling quite a lot of things. Most men would come for help, often Nicodemously at night. I treated them, they were happy, and they rewarded me. I was actually licensed to practice, and I was happy. Well, those were some of the things that I was doing. But the question still remains, is that enough? No, it isn't. The Cancer Association of South Africa actually said that every year we have 700 deaths due to skin cancer every year, we have about 20,000 reported cases, which is really terrible. Now, yet if we look at the drug discovery process, we will see that a lot of years are spent before a drug could be registered, before a drug could be used. It can actually take up to 12 years, 14 years. So the biggest question, and as I said, is out of 1 million of available compounds, which compound is best? And how do we select it? So that is the main question that we want to worry about. Give it some thought. How do we do it? Maybe some may say, well, why don't we go to a Sangoma? Maybe we'll get help. Some may probably say, why not try a prophet? Some will say, well, maybe it's better to do laboratory experiments. I actually like laboratory experiments. And of course, associated with that, we will do it in the test tubes, we will do it in animals, models, humans, and so on. But one problem that we have is we have high costs. Some even estimate up to the tune of 1 billion from start to the end when you get your drug on the market. The time, we cannot ignore that. Remember where I showed you that it may take up to 14 years. So there is a lot of human effort involved. Laboratory experimentation time. We have difficulties associated with animal sacrifice, if you are using animals, and so on. Then you talk about animal welfare and rights. All those are issues involved. Let me just illustrate by picking on 3 examples of drugs which were discovered. Perhaps the first drug that was discovered is morphine, and it was discovered between 1803 and 1817 by Sir Turner. He actually isolated and extracted morphine from the poppy seed juice. And when he was doing the research and the testing, it was so funny. He actually took advantage of rats. He took advantage of stray dogs. So if ever he saw a stray dog, he will catch it and he will do his experimentation there. Worse still, he actually had to self-administer morphine in order to determine the right doses. So you can see in a way that this discovery was really by accident. We have a second case, 1860, Guthrie. He was a very strange scientist who thought that science involved only experimentation and nothing else. He actually synthesized mustard gas, and he noticed that it was actually toxic. And it was then used as a chemical weapon in the World War I and in the World War II. But it then happened that by accident, when Dr. Kruber in 1919 was actually treating some patients in France, he noticed that mustard gas actually had effect on blood cells and bone marrow. And after then people noticed that it can actually be used to cure cancer. So basically, this is how some of the drugs, in fact, how most of the drugs are discovered. And my third example is actually on Viagra. It was actually discovered solely, purely by accident. They were looking for a cure for high blood pressure, administered it to the patients, and the patients actually reported otherwise. And oops, they've discovered Viagra. And during the first 6 months of approval, it actually attracted 5.3 million prescriptions. Thank you very much. Sorry about that, colleagues. I hope you can all hear me clearly. All right, we proceed. So we still have the question, how do we identify? We have noticed that most of these drugs were identified by accident. So the question is, how do we identify suitable compounds? Let me say, in my life as a professor, before that, when I was getting into second year university, we were busy trying to decide on which courses to take. And we had one classmate of ours, known Madiba Chapondwa. He used to like reading novels a lot. And he was knowledgeable during the time. He had gone to college before coming to university. He actually persuaded every one of us and said, well, when you choose your second year courses, please choose graph theory. Who does not know the graph of sine x? Who does not know the graph of cos x? He persuaded us all to do graph theory. And well, we thought that graph theory really involved studying sine x, cos x, x squared, and so on. But we got into the first lecture. The first thing that we were told is a graph is not what you think it is. A graph is not that of cos x. A graph is not that of sine x, but rather simply a collection of points and lines joining some of the points. That is what a graph is. Professor Morris, all my life as a professor, I deal with these things every day. Some are big, some are small. Some are important, but some are not. But I've chosen to do one thing. I've chosen to study those with a meaning. Those that can actually result in applications. So I'm pleased to report that, well, the models that we actually come up with using graphs can handle compounds and formulations accurately as mathematical objects. So all of a sudden, the mathematicians are able to hold compounds in their hands, are able to hold compounds in their own language. And these are basically modeled using graphs. So I really look at graphs that have got a meaning, graphs that actually represent chemical compounds. On the other hand, we also look at the effects of those compounds. For instance, their effectiveness in curing certain diseases and so on. We look at them as mathematical, numerical values. And once we've got the data, we can design a model which does exactly what one wants. So just to give a very short, brief illustration, with my research collaborator, Professor Farah Nyabadza, who is here, well, we decided to look at one property of chemical compounds known as boiling points. So we said, okay, how do we estimate when we are given a compound, any compound known as an alkane compound? These compounds are used in designing fuel mostly. How do you determine their boiling points without going to the laboratory? We know that one route is to go to the laboratory and do experiments and get the boiling points. But we said, without going to the laboratory, how do you determine that? That problem proved to be very difficult. We looked at each other in the eye, and we knew what it meant. Specifically, that it's a very difficult problem. We almost gave up, but we realized that giving up was going to be equated to a soldier who goes out for war. And in the very first sight of death, resigns. We continued to fight. We continued working. It was really hard, but we came up with a model that can actually determine the boiling point of any alkane. And the model, please do not worry, it's not very difficult. And I've also left out some other stuff in the formula. The model simply says, suppose you've got an alkane A, then what you need to do is to compute what we call C of A. That's a parameter. That's a purely graph theoretical parameter. Remember, your A would have been represented in form of a graph. So you calculate your C of A, which we called the conduction of a graph. You calculate your C of A over here, you multiply by alpha 3, a constant, you add a constant, you calculate the logarithm of that, you multiply by sine. I never knew, Professor Chetty, how useful the sine function is. I never knew how useful the logarithm function is. And combining all that with graph theory, it's purely unheard of. So here are two very strange people from two different fields, pure mathematics and applied mathematics, coming up with a formula that will explicitly determine the boiling point of alkanes. So let us take the model to test. Over here, I selected just a few compounds. The compound hexane has a boiling point, and that was obtained through experimentation. It has a boiling point of 68.8 degrees. Now, our model, the one that we designed, says the boiling point is 68.80022, and so on. So you can see that there is no difference at all. If you look at the next compound, its boiling point from the laboratory is 63.3 degrees. Our model says it's 63.299 degrees. The next one, the boiling point is 60.9. Our model says it's 60.9001. So the idea, Prof. Morris, is we wish to cut down on the time that is spent on the laboratory. We wish to cut down on the costs involved through going to the lab experiments. So, boom, now we can actually use that formula to determine the boiling points of alkanes. But this does not involve human life. We then said, okay, let us look at anti-skin cancer. Can we design a model that tells us how effective a compound is in treating anti-skin cancer? We worked on it very hard. It was once again, very difficult. But we managed to get a model that does that so faithfully. And one thing to note is that our model placed a tick on a chemical compound called tropolone, which is a well-known standard anti-skin cancer drug agent. Our model actually confirmed that. It confirmed that this is a cure. This is an agent that can be used to treat anti-skin cancer. But not only that, one interesting thing is that our model discovered 8 more compounds that are actually more stronger than tropolone. And amongst those 8 compounds, the first compound, compound A, is actually 34-fold stronger than tropolone. We then said, look, why don't we also look at other problems? We looked at PDE5 inhibition. We looked at the problem of erectile dysfunction. I spoke about Viagra. And we designed a model that actually discovered new effective compounds. Amongst them, we have two compounds, compound A, which is 3-fold better than Viagra, and we have compound B, which is 2.6-fold better than Viagra as well. And other compounds that we found, which are better than that, are compound C and compound D. It's nice to note that compound C can actually be found naturally in a shrub that is used by the Zulu kingdom as a treatment for impotence. Who would have guessed? Now, the fourth compound can actually be found in the bark of a tree that is used as an aphrodisiac. So you can see that our model is actually picking up things and bringing up new compounds. So one will ask the question, what is the way forward? Well, Wits, Innovation Support Manager at Wits Enterprise, said, well, please do not publish. UJ as well said, well, please do not publish these results, but rather think of commercializing. Not only that, but keep it as a trade secret. I have always been asked by people, can we see it in writing? But, I've always been nervous sharing the results because of that. But, well, that's research. Before I wrap up, let me also say, we were very worried about COVID with my colleagues, Professor Young, Professor Mukwembi, and Professor Nyabadza. We were very, very worried with COVID. So one thing that we noticed actually is that when one is infected with COVID, your body will produce a lot of mucus. And this mucus will actually probably affect your lungs, and you can even die. So we said, well, can't we come up with a model that can look for something that will handle that? And off we went. We started doing research. Professor Betty Young has been doing graph theory for the most part. Professor Mukwembi has been doing graph theory for the most part. They actually have been working with graph parameters. We took some of the parameters and we actually managed to develop the model. And we joined that together with applied mathematics models from Professor Nyabadza, and we got a model. One thing that our model did was to confirm that vitamin C works. But not only that, we managed to identify 3 other compounds that are actually superior to vitamin C. Compound A is 16-fold superior than vitamin C. And during my practice, I was actually using a tree bark to provide a medication if one is infected by things like microbial infection and flus and so on. And compound A can actually be found naturally from that tree, which I will not mention unless if you give me a glass of wine. Well, I'm pleased to note, Professor Chetty, Professor Morris, I'm pleased to note that as we speak, these compounds are in the laboratory. They are testing those, for confirmation. Now, technology innovation agents, Commission of Developing Countries, in conjunction with the International Mathematical Union, also weighed in. They actually gave us funding to do some of these projects. Currently, as we speak, together with Dr. Marume, Dr. Mtingwende, Prof. Nyabadza, Ms. Paddy, And Professor Fei said, we are actually developing a model that will identify compounds that can be used to treat COVID. We have a model and we now have the required compounds. Professor Morris, I really like sharing knowledge. I really like disseminating this information to the community. My postdoc student, Dr. Alochuku, Professor Young, Professor Mpakobanda, and Professor Nyabadza, and of course, Professor Fandamerwe, are actually working on developing a model that can best identify compounds that will handle metabolic diseases. We all know that as we age, just like myself, I'm perhaps towards aging, you will suffer from various of these metabolic diseases. So we are actually developing a model that will help us get compounds that can handle that. Well, thank you very much all for coming. Thank you for attending to my talk. I rest my case.
Thank you, Professor Simon Mukwembi, for your intriguing inaugural lecture based on your current research, showing the importance of mathematics in driving innovations with impact on society. Very much appreciated. Ladies and gentlemen, I would like to call upon Professor Betsy Young to move the vote of thanks. Professor Betsy Young did her undergraduate studies at the University of Pretoria and her postgraduate studies at the University of Johannesburg, previously the Rand Afrikaans University. She taught at high school, Die Fakel, from 1980 to 1992, and was a lecturer, senior lecturer and associate professor at the University of Johannesburg, 93 through to 2016. From 2016, she has been here at Wits University, where she served as head of school. She became full professor in the year 2019. Professor Betsy Young, please deliver your vote of thanks.
Professors Morris, Chetty, Kara, the organizing committee, and all our guests. It is with pleasure that I give this vote of thanks. I know Prof. Simon Mukwembi from conferences of the South African Mathematical Society, SAMS. Prof. Peter Donkelman, Simon's ex-PhD supervisor, encouraged me to attend Simon's interesting and entertaining lectures at SAMS. Simon as person is all about pure kindness, positiveness, open-mindedness, and steadfastness. Moreover, he has a marvelous sense of humor. For example, we co-supervise, amongst others, a master's, a MSc student, who is himself actually a master at evading us. At scheduled meetings, we are there as supervisors, waiting patiently for him, because as Simon said, he just may miraculously appear. For another example, please ask Simon about the demolition van that demolished his car. Mathematically spoken, He is a go-getter. His undergraduate studies was at University of Zim and his graduate at UKZN. Prof. Chetty told you also more about it, but I just want to mention that at UKZN, he climbed the ranks from lecturer to associate prof and academic leader in 8 years. At the University of Zimbabwe, 2 years later, he was a full prof, the head of school, and deputy dean. He published widely, wrote articles, chapters in books, and a book. He completed supervision of 8 doctoral students and a number of master students, and currently he is supervising 2 honor students, 6 master students, 2 PhD students, and a postdoc. He attended a number of 21 national and international conferences, external and reviewed many times. As Prof. Chetty also said, his international standing is high. He has a Google Scholar H index of 17 and is cited a lot of times. I believe that Simon Mukwembi will leave a lasting impression here at Wits, as he did at UKZN and as he did at the University of Zim. Thank you.
Thank you very much, Professor Betsy Young, much appreciated. Deputy Vice Chancellor, ladies and gentlemen, also colleagues who have joined us online. I should have mentioned, it's just so wonderful for me to do this inaugural address for the very first time in person. I've done quite a number of these over the past 2 years, and it's just such a delight to be amongst you. Wish now to close the proceedings and invite you all to some refreshments that have been arranged out in the foyer. Have a good evening. Thank you now.